All right, so here we go here with our next type of KSP problem. And again, the reason for these different types of problems that I've selected is to give you experience in the different ways that we go over these equilibrium problems. So by giving you the worksheets, and hopefully you're completing all of them, you get the full spectrum of the types of things you can see with equilibrium problems, or solution equilibria, as sometimes it's called when you learn about KSPs. Still tied to delta G, thermodynamics, okay, the movement of a reaction in a certain direction toward equilibrium. Okay, so here's our next and final experience with KSPs, or solution equilibrium, okay? So in any case, here's the question. What's the molar solubility of strontium sulfate in pure water? Now, as I've told you, KSPs are nothing more than equilibrium constants for a solid breaking apart into its ions. So sometimes it's helpful to see that, all right? So sometimes I'll write, okay, that means that strontium sulfate, and let's not pick the red, all right? Strontium sulfate dissociates it's a solid. It dissociates and produces solution equilibria with its ions. Its ions are strontium plus 2 and the sulfate ion, SO4 negative 2. And these are aqueous, so we can write little AQ here. Okay, now that gives me an idea what's going on. Now, what are they saying? Well, the KSP for the equilibrium constant for this equilibrium, for solution equilibrium, is 7.6 times 10 negative 7. That gives you an idea about the solubility, doesn't it? Higher the KSP, right? K, EQ or KSP or Ka or any type of equilibrium constant is the products over the reactants to their coefficients, solids and liquids don't apply. So this value gives us an insight about solubility. You would say, oh, okay, higher the KSP, the more ions you have because the ions are products. Okay, and so you can evaluate strontium fluoride is 7.9 times 10 to the negative 10. Is clearly less soluble than strontium sulfate, who is 7.6 times 10 to the negative 7. The reason why strontium fluoride is less soluble is because it's got a smaller KSP. A smaller K means you have less products, okay, at equilibrium for that temperature, temperature dependent. And because you have less products, and the products are the ions, clearly this is less soluble. This is more soluble by 1,000 times. Okay, so it's got more ions dissociating. So what we're going to do is to come up with a value that tells me exactly the solubility. Although the KSP gives me insight to who's more soluble, it doesn't give me molarity. Okay, so what I'm going to have to do is, to find the solubility of strontium sulfate, I have to actually find the molarity of one of its components. I can't find the molarity of the solid because there's no molarity of a pure solid, so I find the molarity of one of these guys. So all I do is I do a Ksp expression. Okay, so Ksp is going to be equal to products over reactants, coefficients become exponents, solids and liquids don't apply. So what we have here is we have strontium sulfate, okay, which we don't use, and we have just the product of the ions. That's why it's a solubility product. So strontium plus 2, and we have sulfate, SO4 negative 2. And because there is no coefficients here, it's a 1-to-1, okay, then we have, of course, coefficients of 1 here. All right, well, what did they give me? Well, they gave me the KSP. They were nice. So in the last question we did, we had to come up with the KSP. So this is just looking at it from the opposite direction. So the KSP for this is 7.6 times 10 to the negative 7. To the naked eye, which is weird, when is an eye not naked, but okay. To the naked eye, it looks like strontium sulfate is clearly insoluble. So there's strontium fluoride, but there is more ions when it's saturated for the strontium sulfate. Now, we're going to solve for one of these. Doesn't matter. And because, well, each one is going to be what? Well, yeah. Now here's what I want you to eventually move toward. In a This is a 1985 Part 2 question. You're not going to have time to write an equilibrium table here. But if you don't see what we're doing, early on you should do this. So let's do an ice table. You don't have to do it, just watch me. Because honestly, you should get to the point where you don't need the ice table for some of these. Okay, clearly, initially, all right, we would have 0. If we started with 100% strontium sulfate being added, the change is what? Plus x, and this would be plus x. Why is it plus x? It's 1 to 1. And of course, x plus 0 at equilibrium is just what? X. You probably didn't need to spend a minute to do all that to realize that this is x and x. Okay, so some of these ice tables will be intuitive. Clearly, it's x and x. Okay? But if you have to initially, be my host and do that. So you got x and you've got x. Okay, clearly it's x squared is equal to 7.6 times 10 to the negative 7. Okay, so we take the square root of both sides. And my calculator is where? Right here. So we take 7.6, second function. Stay away from the caret key, party people. I just keep trying to help you get that and do the square root of that. Second answer. Okay, I get 8.7, or x is equal to 8.72, or 8.7 times 10 to the negative 4. Now what is that? Well, my friend in chemistries, that is your value of the solubility of either the sulfate ion or the strontium ion. Make your choice, who cares? But the bottom line is you just came up with the solubility of strontium sulfate. Because it's a 1 to 1, there's one strontium per strontium sulfate, or there's one sulfate per strontium sulfate. That is the solubility of that compound. So that's your answer, okay? And you can write it many ways, and that's good enough for me. And that of course, would be a molarity, all right? Because remember, brackets represent molarity. So there's your answer. All right? Let's go on to the next one. All right, next reaction, we have SRF2. So we got this. We have strontium fluoride, which, by the way, is insoluble to the naked eye, because that fluorine really is so negative and so small, it has a high charge density. It's going to break apart into Sr plus 2, alkaline earth metal. But in this case, 2 fluoride ions. Of course, they're aqueous. Aqueous. All right. Now, same problem, isn't it? Ksp is equal to, in this case, the concentration of the strontium plus 2. And now you have the fluoride ion, but what's different here is what? Products over reactants, coefficients become exponents. And because you've got a what? 2 fluorine, this is squared. Bless you, meant it. Okay? All right. So, if you need to do this, you can. All right, so a quick ice table, if you don't see it, it's okay, but at some point you need to move away from the ice table for these. 0, 0. This would be plus x as we go forward. If you have nothing initially, this would be plus what? 2x. That's a big deal here. So at equilibrium, it's 0 plus x is x. 0 plus 2x is 2x. At equilibrium, we put these values. What's the Ksp that they gave me? 7.9 times 10 to the negative 10. And that's going to equal x. And this is important. This is 2x. And it's squared. How many times I've been teaching these types of problems, and I've watched people put x squared here. Say, oh, the square is there already, so I just put an x here. This is a relationship stoichiometrically from what? From the compound dissociating. There's clearly 2 times the amount of fluoride ions compared to this formula than it is to strontium. So the relationship of what's being gained when it dissociates is how this relates to each other. And of course, all right, the square is a result of using the dilution derivation that I showed you that got us to what KQ represents in terms of concentration changes, or Q. Entirely two different pieces, okay, that are there. If I gave you the concentration of the fluoride ion, that would be it, but we don't have it. So as it relates to strontium, it's twice as much. Okay, now we just solve for it. All right, so clearly I get what? 4x squared times x, and I get 4x cubed equal, all right, 7.9 times 10 to the negative 10. Everybody see that? Okay? Squaring this gives me 4, squaring the x is 4x squared, and then 4x squared times x is 4x cubed. Okay, how do we solve for the x? We cube root it to both sides. So on your TI-80, I believe, I think it's math, you gotta do the math key. You guys know this better than I do, I'm sure. And I do, I think, math, and I do 3 of the, oh, it's cubed. No, that's not what I want. I want math, I want the cube root, so that would be 4. Second answer, close my parentheses. Okay. Please chime in with nice chimes if I make a mistake here. So I get my x to equal, all right, my x to equal 9.2, 24, we'll do 2 significance, 9.2 times 10 to the negative 4. What does that represent? That represents, okay? Oh, I did make a mistake. Yes, I did. Because you're not just cube rooting, you got to divide by 4 first. Okay, because you're solving for x. And I made that mistake, and I knew that someone was going to make it, I just didn't know it was me. So yeah, so we got to divide by 4. So to take your 7.9, I knew it was a mistake made. I was like, I got myself. All right, 7.9 times 10 to the negative 10. We got to divide by 4 because we're solving for x cubed, so you just can't cube root both sides yet. So divide by 4. Okay, then you cube root it. Easy for me to say. Number 4, second answer. Okay, 5.8 times 10 to the negative 4. Does that sound better? I'll take that as a yes. So x is equal to, after I divide by 4 and cube root both sides, x is equal to 5.8 times 10 to the negative 4. Okay, what does that represent? That represents the value of x at equilibrium concentration. It's a molarity, so I should put that there. All right, and that's the answer. Now, why is it the answer? What they asked for? What's the molar solubility of strontium fluoride? Isn't there, well, we found the solubility of strontium at equilibrium. Isn't there 1 strontium per strontium fluoride? Yes, so that's the answer. What if they wanted the molar solubility of the fluoride ion? Times by 2 and square it? No, just times by 2, right, right. Okay, absolutely right, we just doubled that. Okay, so be aware of what they're asking. They want the molar solubility of this. We got this value, and there's 1 of these per 1 of these, so it's the same value. Be aware of that, okay? All right, so that's A and B. Probably 2 points apiece here, at least, for these 2 questions, okay? And not very difficult, but this is how we actually get the solubility or the value of at equilibrium. What is the maximum concentration of these ions at equilibrium for that temperature before it starts to what? Precipitate. Think of it that way. Okay, letter C. And this is another new way to look at these problems. Letter C. I got an aqueous solution of strontium nitrate is added to slowly to a liter of well stirred. Now, well stirred, okay? Solution containing 0.02 moles of fluoride ions and 0.1 moles of sulfate ions. Oh my God, so much data. What are they talking about? Well, they give you the temperature to remind you it's the same temperature everything's based upon. but we're pouring two solutions together. If you've got to draw yourself a diagram, okay, what are we pouring? We're into one beaker, okay, we're pouring what? We're adding strontium nitrate. Now, what are they really telling you by strontium nitrate? Nitrates are always soluble. So what are they telling them? I'm adding what? I'm adding strontium plus 2. Okay, so an aqueous solution is added slowly too. So I'm adding strontium plus 2 ions. The nitrates are spectators, so get that. Now you're adding it to a liter of well-stirred solution that already contains what? Fluoride ions. Okay, so you already got F negative hanging out here. And you also have sulfate ions. So get some room here. SO4 negative 2. So we're adding strontium ions. Now how does this relate to the first question? Well, the first question gave you a Ksp for strontium sulfate. The second question was strontium fluoride. So clearly, as I pour strontium ions in here, two precipitates are going to occur, correct? Yeah. Now the question is, who precipitates first? That's the question. They're both going to precipitate, all right, but you've got to calculate which one. So how do we go about doing this? Well, let's do the strontium sulfate. Let's figure out, okay, using this information. Now, what they're saying in the problem is, normally when you add a solution to another, you dilute all the solutions. But they're making this easier by saying, assume that this does not affect the total volume of the system. This could be a huge vat of this, and the stuff you're adding isn't significant enough. They're making that easier. So it's an important piece there, because that's not there. You're going to have to dilute these. And in fact, you would actually need calculus, I believe, to solve this, because you have a simultaneous equation going on. Okay? As you're pouring, you're changing the function of these solubilities as you pour. So it's not a linear equation anymore. Any case, so moving forward, let's go through strontium fluoride first. So here we got strontium. And just rewrite this to see what we're doing. Okay, of course, it's in equilibrium with its ions. So it's strontium plus 2. And of course, it becomes what? Sulfate negative 2. Now I'm being redundant here. You don't have this time on a real test, but I'm just making sure we understand it. Okay, now what's my Ksp? My Ksp again is going to be equal to X times X. And what is my Ksp of that? My Ksp is 7.6 times 10 to the negative 7. So 7.6 times 10 to the negative 7. Now, we don't really have an X there. Let's go back to the question. How much of this do I need to make this precipitate? Well, how much sulfate do I have? They say I have a 0.1 mole sulfate in a liter solution. Remember, this is a bracket. This is a molarity. It's an easy question because 0.1 moles over 1 liter, that's the molarity formula. So what's the molarity? 0.1. So I'm going to get rid of this X here. And I'm going to put 0.1. That's going to, we get that from the problem. 0.1 molar. Okay. So that's already there. So think with me for a second. I've got the sulfide ions in there. There's no precipitate because there's 0 sulfate. Because there's 0 strontium. Because there's 0 strontium, your Q, think about Ksp is here. Your Q is up here. So how much strontium do you have to add? And as you add strontium, your Q becomes what? Bigger and bigger and bigger until it equals the Ksp. When it equals the Ksp, you're at that threshold. Anything greater, you have what? Backwards movement toward the precipitate. Remember, keep thinking in terms of this diagram. All right? Here's your Ksp. Your Q is right here. It's too small. Q is products over reactants. You have too many what? All right, at this point, no products. Okay, well, you have a 0 here. So this makes your Q become 0. Now, as you add strontium with this here, it starts getting increasingly larger to the point where you match this. And anything above that, you're going to have an equilibrium or spontaneity. Delta G will be negative in the reverse, and it'll happen. So I want you to think that way. All right? So, what do? We solve for x. Solving for x, what do we have? Where's my calculator? Oh. So, essentially x is going to be 7.6 divided by 0.1, so what do we get? 7.6 times 10 to the negative 6. So we get x, or we get the strontium plus 2 is equal to, we're dividing by 10, right? So this becomes 7.6 times 10 to the negative 6 molar. That is what we need to make it equal to Ksp. Anything bigger than that with this value here gives us what? A value where the Q now is going to be bigger than Ksp and precipitation occurs. That's the threshold, right? That's a big number compared to this. All right? Let's do the second one. I'm going to keep you until I finish the problem. I'll give you a little break. All right? So, let's do the second part of this. Let's do the strontium fluoride. Don't know why I got a line going through. Why did that happen? That's bothering somebody. So let's go blue, strontium fluoride. Ooh, too thick. Can't do it. Breaks apart into watt. Strontium plus 2 fluoride ions. I'm just reminding myself not to make a silly mistake here. And of course, the Ksp is equal to what? X times what? 2x squared. All right? What is my Ksp? My Ksp is 7.9 times 10 to the negative 10. So 7.9 times 10 to the negative 10. Solve for x. Okay? Well, the deal is we have a value. Oops, sorry. So it's not really 2x there, and this confuses some people. They're telling you that there's a fluoride ions already in the solution. How much? There's 0.02 moles of it per 1 liter. So, my friends in chemistry, the 2x, we don't multiply that by 2. That is the actual concentration. Okay, so it becomes 0.020 molar. Why? Because molarity is moles over liter. Here's my moles, and I'm over a liter. Okay, so I don't double that. That is the actual value. Okay? It's when I don't have any information, I double it, compare it about how much this value. So don't get confused with the 2x. That is the actual. That represents the 2x. Okay? Now, what must be the other value? Well, we solve for x now. Okay? So we're going to square that, which is an easy one, right? If you were doing this on a test, okay, would you put this in your calculator? Maybe you would, because maybe 0.02 squared, okay, you should get 0.0004, right? Okay, sometimes those kind of things you can do fast. If not, who cares? All right, any case, you're taking your 7.9 second function, I'm sorry, I shouldn't speak out loud, and I'm dividing by 0.0004. Okay, and I get my x to be 1.96. So x is equal, or my strontium ion concentration, and let me just make that a different color. My strontium ion concentration in this equilibrium, for it to reach that threshold value, that anything greater than that will cause you to be Q to be larger than K and have precipitation, is equal to 1.96 or 1.9 or 2.0, 1.98, however you want to think of it, doesn't matter. I'll just do 1.98 times 10 to the what? Negative 6, and it's molar. Okay. Now doing these two, everyone see what I just did? I found what would the strontium concentration would be for each of these. Pouring strontium ions in for some concentrations of fluoride ions and sulfate ions already given to me, based on the same temperature, and using my equilibrium of how much has to be if this is the value here. knowing the Ksp, solving for what the strontium concentrations have to be for each equilibrium, each precipitation reaction, I can clearly see as I'm pouring which value do I reach first. Right, this is a smaller value. So as I'm pouring, I'm going to hit the threshold value for this one first. This is the one that's going to hit the equilibrium position first because it's smaller. Right? As you pour strontium ions, you go from 0 strontium ions to 1, 2, 3, 4 to some amount of ions. And you're going to hit this concentration first before you hit the larger concentration. Does that make sense? Yes? Ja oder nein? Okay. So this tells you that that is the one that's going to precipitate first. So you would say strontium fluoride precipitates first. And they may say, in some questions they say, support your answer. And you would say, if they said support your answer, you would say, because this one's a smaller value, this is the one that the strontium would hit first as you pour. It's the one it reaches first. Yes?
Wouldn't you have just gotten that from the first part of the problem, where it said that strontium fluoride had a lower Ksp?
Not necessarily. Now, I know what you meant. Just looking at the KSPs, and it's a great question. You may say, well, the lower KSP, okay, would do it because the lower KSP is the one, is the one that's insoluble. Okay. However, the factor that changes everything is how much of the other salt. So you just can't look at the KSPs alone. You have to do this. It did work out in this case that the one that was the least soluble would precipitate first. But if I change these values, think with me, that equilibrium position is fixed at a certain temperature. How much of this, if this is big, this has to be small. So if this was a much smaller number, I'm sorry, if this was a much bigger number, this would have to be much smaller to reach that number, right? It's the amount of these two have to be in some amount to equal this value. So it was this factor that you started with that really drove the answer. Yes, this salt is more insoluble, but if I change these values, it won't always be this salt.
Yeah, no, I was just thinking because it said that there was more fluoride than arsenic, so wouldn't it be kind of, as soon as you knew that there was more fluoride, you could just assume that it went the same way?
I guess there is more, there's less fluoride.
Oh,
Yeah, it's less fluoride. You really have to, I mean, it worked out in the way that you'd expect intuitively, but it may not always. You're going to have to do the math to see, because again, how much you have of this drives this one down. It's low, this one. So we're looking to see what these values are. So the factor, yes, that does give you some insight, but this is what you needed to do. It's a good point. Okay, excellent point. And just by KSPs alone, you needed to know how much of these. Yes, it did work out the way you thought, but you needed to figure that out. Because if I'm writing the problem, I wouldn't make it work out the way you thought. Okay, but it did here. Okay, so in any case, number 2. Of course, I don't write these problems anymore. These are all someone else's, so they're going to be more straightforward for the most part. Yeah, I mean, I've given these guys questions, but they've always, I've been turned down. Okay, 2. What is the concentration of strontium ion in the solution when the solution first begins to form? Okay, obviously, we just found it, didn't we? Here it is. What is the concentration of strontium? So maybe in some other way you did this. Okay, I don't know how other way you would have, but this is the concentration you would use. So this is probably a question that's built together somehow, and there's the answer. Okay. All right. Letter D. A lot of space for an arrow. Sorry. And then letter D. As more strontium nitrate is added in the mixture, a second precipitate forms. Obviously, that's the strontium sulfate. Okay. At what stage, what percent of the anion in the first precipitate remains in solution? Well, the anion always means negative. So the question is, and it sounds strange, but it's not that difficult. As I keep adding strontium nitrate, this is precipitated. Why is it precipitate? Because it's got you're making this X too big, and eventually your what? Q is greater than your K, and therefore you're going to make precipitate. It doesn't mean that all of the F is going to disappear. You're going to reach an equilibrium position, but as you add more strontium, okay, you start driving this reaction this way, as we learn in Le Chatelier's principle. So the F is going to get smaller and smaller and smaller, but it's not going to go to 0 because of the equilibrium that it's established at that position. However, what is that, that percentage? Well, percentage is part over total, okay? So what at stage, so here's the question. At that stage, what percent of the anion of the first remains in solution? All right, well, I know that the total amount of the fluoride ion is 0.02, 0. I got to find what's remaining, and I times that by 100, okay? And I find my percentage. So let's look at the when the second precipitate begins to form. What's the strontium concentration? 7.6. So when this starts, the strontium concentration is exactly that. So I want to know how much F is existing when the strontium concentration is 7.6. What do I do? Right. This is the concentration of the strontium ion when it precipitates. That's the value of the X. We solve for that. And I'm going to put this value here. And that's going to tell me how much F is remaining. Because you make this bigger, it's going to drive more F into what? The precipitate. So plug that in. So I want to do that math here since I have the room. So 7.9 times 10 to the negative 10, that's not changing because the what? The temperature's not changing. What is the value of the F negative? Oops, no, bad Grotsky. What is the value of the F negative when the strontium concentration is 7.6 times 10 to the negative 6? So what is my F? What's my F negative? And of course, don't forget it's squared, so you can put that X in there if you'd like. And we're rocking and rolling. Okay, we solve for this. We're going to divide by 7.6 times 10 to the negative 6. So we do some math here with a handy-dandy calculator, 7.9s. You guys banging away, it's kind of cool. Okay, to the negative 10. And then take the square root, both sides.
Would it be 2x or just x?
Great question. I'm solving for this amount, okay? I'm not putting 2x here because 2x is what you would need stoichiometrically in a problem. If I was starting from 0 and there was something moving forward in an ice table, you would make double that what this would make. It's not what we're doing here. What we're doing is, what is the value of this? I need 2x when I compare it to how much the product or the reactant is losing to go this way stoichiometrically. I want to find what is this concentration. So I'm just finding this value. Right? You need 2x when you consider that this breaks apart into one of these and one of these, or one of these and two of these. Okay? So we're not putting 2x here. This is just the value. It's a great question. How much of this do I need? Okay? So I'm just solving for what this is. Okay, it's different. All right? So second function, second answer. And I get 0.01. So my x, after I divide by 7.6, take the square root of both sides. Okay, we should have figured that out. I get x is equal to 0.010. That's the molarity of the fluoride ion that is remaining once this number jumps up to that and drives that forward. Well, you can do the math in your head, can't you? So what is 0.01? 0.01 is what's left for the fluoride ion molar, and you started with what? 0.020, obviously, times 100, that's 50% is remaining. All right? And that was a very, very good question you gave me. Okay, because I know people want to throw the 2x in here blindly. 2x is a relationship based with this as we go forward. Remember, we added this in from another source. Brandon, let me answer your question better, because everyone makes that mistake too. They want to throw the 2x in because it was 2x. If I had this salt, the salt, and as I dissolve some of it, whatever this is formed from the salt, I would produce twice as much. That's the 2x. We're adding the strontium not from the salt. The salt produces one of these and two of these as it dissociates. In this problem, we're adding the strontium not from a salt, from another source. So we're adding the strontium in not from this dissociating. If it did, you're right, it'd be 2x. We're adding the strontium in from an other source, so that becomes whatever value it is. We need to figure out what this value would be based on that. If I was considering what happens when this goes forward, yes, 2x, because every one of these produces two of these. Okay, it's a great question. But we were just evaluating what this has to be, adding this from a independent source other than this. This 2xx is a relationship of this going this way. Okay, hopefully you can see that. All right, any questions? All right, that's a very typical, and that's the last bit. I've given you questions now that go over all different ways you can see KSP problems. So what we're going to do now is classwork or homework. Okay, if you want to give an insight of what an AP question looks like, we'll be looking at them. So if you look at 5B, that's your homework or classwork. You want to give yourself some time to do that? There's some practice. I'm giving you practice upon practice. So you can start that now. Let me figure out the time period. So 5C is next, and that'll be your homework, classwork, or whatever you want to do now. But that'd be a great sit down, do that problem in its entirety. I have the key, I'll post the key, I think, and you can figure out. So there's a typical. Now these questions were old AP questions that I put into a ditto form, meaning I kind of broke them up into questions. That is how you would see them. Okay? And you may begin those. Hi, Bryce.